Zaline De Pas. I'm the team leader of technology department, department, and I'm delighted to welcome you to our webinar on in situ and ex situ thermal desorption, the technology evolution to a more sustainable soil treatment option. So this is a crucial, innovative, and current subject that we are presenting to you today. This webinar will approximately last 45 minutes, so presentation during 30 minutes and followed by 15 minutes of Q&A session. So don't hesitate to ask your question in the chat box. Your microphone is muted to avoid any interruption. I'm delighted to introduce our speaker of the day, so Jan Ammers. Jan is the CEO of Ammers Technologies and has spent his entire career in the soil remediation world. And now, Jan, the floor is yours.
Well, thank you, Isaline. Well, good afternoon or good morning to everyone. Indeed, it's my pleasure to address this subject on thermal desorption. So the purpose today that I'm just going to cover with you over this 20, 30 minutes is energy. And it's called, the title was initially sustainability. And we will see that the whole idea is to focus sustainability on energy and the common misinterpretation or misconception that we hear all over, say, oh, thermal desorption, yeah, it's a nice technology, it's very efficient, but it's it's a lot of energy, and is it really sustainable? So I'm going to really address it head on. And so let me start sharing with you the agenda. But before that, a very quick summary slide. This is something we are overall relatively proud of as an industry in thermal, and that is the evolution over about, say, 25 years of energy consumption. In the late 90s, started doing thermal in the early 90s, but in the late 90s, we were consuming almost 600 kilowatt hours per ton of soil to be treated thermally. What you see there are two lines. The one is blue, the other one is green. The blue is, we say, with higher temperature, so reaching above 100 degrees, typically hydrocarbons, pHs, dioxins, etc. And the green one is when you have to clean up chlorinated solvents, BTEC, so low temperature, when you don't have to go above 100 degrees. And that will be part of the rest of the webinar today. But you see that over the course of 25 years, the total energy consumption per ton of soil has been divided almost by 3. So it is something that went mostly unnoticed, but I think it's time to just remind everyone that that is the reality. The consumption has gone down dramatically. On the other hand, when you look at equivalency on treatment, you could say, well, let's dig and dump. Let's excavate my soil, bring it somewhere else, replace it with new soil. It's the comparison or the alternative between linear and circular economy. Linear economy is I use my soil, I contaminate it, and now I throw it away and I replace it with new one. That is linear economy. That's dig and dump. Alternative is indeed recycle, reuse the soil, and that is what we will do with ISTD. So the same result at the end, but as you can see, not that same level of progress. And today, I think we can be very proud, and I'll finish it with a clear example, that we have reached the level that we are equivalent, sometimes even lower in consumption than dig and dump. Dig and dump meaning excavating, transportation, bringing back clean material, no treatment. So it's displacing the problem versus actually treating the problem and still consuming less energy. I think this is something that would be the key driver to this webinar and this presentation, but that should be known and hammered because there is a lot of historical misconceptions and people thinking about it and not actually looking at the numbers. So yeah, we're engineers, we're looking at numbers. So I'll briefly introduce it, and we'll talk about energy as part of sustainability. It is a key part, and then we'll dig deeper into the key drivers. Why is it so essential to understand that design can be actually the reason why we have gone down that much. I will close up with a concrete case. I just see that I forgot to cut down my phone, and I want to do that right away so that we're on our own and nobody's going to disturb us. Brief introduction of the company for those of you who don't know us. We're a small company. We're based here in Brussels. We have operations in the US and in Europe. We're, of course, European based as an origin. We're almost completed 80 projects in thermal desorption, conductive heating with 54. We have a pretty diverse team, as you can see, with 17 countries of origin, of which we're pretty proud, and we operate with partners all over the world, typically by transferring technology and working with them on the implementation side. So let's dig into the subject of today, energy and sustainability. Here is just to give you an idea what how much energy it takes to excavate and how much energy it takes then later to transport. We know easier, but excavation is something that is overlooked. The deeper you go, and unfortunately it's still in feet, but essentially 20 feet, say 7 meters. If you're that deep, see how steep the consumption goes for your excavator. And the deeper you go, the more you're going to use to excavate soil. And I don't know, you know that, but people tend to forget that, excavators, they don't run on lemonade. So they also need fuel. So when you come to roughly 180 kilowatt hour per ton, that is how much it will take you to excavate 1 ton of dirt at 6 meters deep, transport it 80 kilometers and bring clean soil back and put it back at 6 meters. That's the amount of energy that is used, 180 kilowatt hours per ton. And it is substantial. People think to forget about it, but it is substantial and it's key. Of course, energy prices have gone through the roof last year. Now they're pretty low again, but the lesson we learned of it is that energy prices are very variable. So they can go any direction. And it's the first answer to that from a sustainability standpoint is to reduce our consumption. In a second step, that is the absolute needed energy to make sure that that energy is as green as possible. So in other words, rule 1, how many kilowatt hours per ton? That should be the minimum. And then make sure that the kilowatt hours you use are as low carbon as possible. But don't do the common mistake, which is saying, I'm going to use more, but it's going to be green energy. That's a common mistake. And I think it's wrong, because if you use more energy, but you say, oh, it's green, so it doesn't matter. No. The energy that you could save is actually going to be used by someone else, and that would be gray energy. So no, that is what we would qualify as typically a bit of greenwashing. So let's continue on our journey towards energy. Already 10 years ago, thermal was considered as more sustainable as excavation, albeit with higher energy consumption. More sustainable. Why? Because it delivered a more circular approach. Because by cleaning soil in situ while reaching the same result, you didn't create the same disturbance. You didn't have to excavate. You didn't have to cause hindrances and transportation and risks on the roads and consume clean materials, etc., etc. You didn't have to do that. So that was a big advantage of having it in situ, which provided in situ thermal to have much higher sustainability scores than the alternative of dig and dump. Today, it's even better because we're even better on the energy standpoint. Right, so that's the message on energy and sustainability, so that we can really excel on that part. Now let's go into consumption itself and how it works. That's the core of my presentation today. Energy usage. So we're going to focus we're going to start from let's say theory, and we're going to focus on a volume of soil. We consider volume of soil in this case pretty simple to see, 2020 by 6. So 6 surfaces, this is the base we're going to look at, and we're going to consider how can we heat that up, and how much energy will it take, and what's the design. So we're going to consider the Vado zone, and we're going to consider no influx of water, so a relatively simple system. The whole point is to reach a certain temperature and so that the pollutants are mobilized by being transformed into vapor phase, and then to extract it. That's essentially what we're going to try to reach. So we see that energy requirements, they're independent of the heating technique. No matter how you heat it, it's a matter of how many kilowatt hours or joules or BTUs, whatever you need to use, but how many kilowatt hours you need to heat a certain volume. If we're in this room and we need to bring this room up to, say, 30 degrees and we're at 20, it's how many kilowatt hours would be needed would not make a difference whether we heat it with a fire or with a radiator or with an electrical heater. It doesn't matter. It's the amount of energy we need. And that also will depend on the soil characteristics. That's the main factor. So what type of soil we have, how much water there is, we'll see that will be the main one, and what type of contaminant we have, because that's the essence we need to heat. Of course, if we had to heat air, it would take way less energy than if we have to heat solids. And in this case, we'll have to heat both air and solids. Oops. Let's go. So let's assume we're in a perfect world. We want to go from 10 degrees to 100 degrees. Okay? We have soil. Typically, it's at 10 degrees. We want to bring it at 300 because we think once it's at 300, it will be clean because of contaminants will be mobilized. If we do that, in the Vado zone, we consider no incoming water. We consider very common and usual porosity, 35%. Typical density, 1.8, 16% moisture. That's in mass, so it's 16% water based on the total volume. If we do that calculation, we'll end up at 1.22 billion joules per cubic meter. So bottom line, it's about 180 kilowatt hours per ton. If you do that on a per ton with that type of density, for the people following this in I think the last country that uses that imperial system in the US, it's about 56,000 BTU per square foot, per cubic foot. These are all the data that go into the model that deliver us that number. So that's in a perfect world. So keep in mind about 170, 180 kilowatt hour per ton. That's in theory. So now, do we live in theory? Unfortunately not, but still it's important to look at what the mix about that is. The amount of energy we need to use is, as you can see here, for more than 50%, in this case 55%, is used to evaporate water. So to go from 99.9 to 100.1 degrees. That's where the bulk of the energy is. And remember, my first slide was that difference between the blue and the green line, the fact that reaching 100, above 100 or below 100 degrees, that is why there is such a big difference. That's why it takes a lot of energy to get that water out. 27 degrees is to go up to 100 degrees, and then 17%, at the end is just to go from 101 to the target temperature in this model was 300 degrees. So gives you an idea of how important moisture is in our model and in our energy consumption. Then you'll see it in this graph that shows. We'll see what this means, distance between pipes or energy density, essentially. So it's a design parameter. But you see how long it will take to reach a temperature of 250 degrees, right? How many days it will take. And all these lines depend on how wet the soil is. You go from very dry soil, 5%, to relatively wet soil, 20%. And you can see, for example, if we take a design with 2.5 meter interdistance, we'll get to that just in a bit. But for dry soil, we're done in 40 days. For wet soil, it's going to take 105 days. All other things being equal, this is how important water is. So this is why water content drives energy, and anything we can do to reduce moisture content in the soil is going to help reduce energy consumption. It's the main driver of energy consumption. Now, as I said, we started the model with a perfect world. In a real world, there are losses and inefficiencies, right? Losses and inefficiencies is that the heat doesn't stay. Where are the losses and inefficiencies? The first is energy production. We produce energy usually from primary energy. It's either solar, it's fossil fuels, it's secondary or green fuels, biofuels, can be geothermy. I mean, it comes from a primary source. And in order to get energy from that primary source to your soil, there's going to be a loss in production. Then there is, next to that, there is the transfer efficiency to the soil. Once it's at the site, you still have to transfer it into the soil. There is going to be a certain loss and a transfer efficiency. And then there are losses at the boundaries. We heat up a volume, that heat will get out of the volume. So everything that goes out of that volume is a loss, right? So these are the three main ones that will drive our efficiency. So energy production, it will mainly be driven by conversions. The more conversions in energy we have, the less efficient it is. Conversion means you have, thermal energy, so heat. Then you convert it in mechanical energy. You convert it in electrical energy. Every time you convert, you're inefficient and you have losses. So that's what will drive the total, let's say, footprint of total consumption you have. Of course, we're going to get into the transfer efficiency to the soil, and then boundaries. You have a volume, especially in situ. If your volume is hot, where does that heat go? It can go on the top, right? Which is something, it will be hot, so you will have losses. It will go at the bottom, at the sides and the bottom. Of course, it will heat up outside of it, and that's a loss as well. So we'll have to figure that out and factor that in our design. So let's first dig into the energy production efficiency. It's a key element. And let's distinguish primary and secondary energy. I've heard a lot of discussions about, yes, but electricity, is that better than gas? It's not better. It has nothing to do. Electricity is not a primary energy. Electricity doesn't come unless you're Zeus and you're the god and you master lightning. Other than that, electricity does not come naturally. It's the result of a transformation itself. You have to go into the primary energy that makes electricity. So by and large, if you want to have electricity delivered 1 kilowatt hour, it will require about 3 kilowatt hour of natural gas or diesel or coal, because you're in the range of 30, in the mid to high 30s in efficiency, where that primary energy of natural gas is transformed into electrical energy. Same thing in nuclear, because you go, and it's logic. You transform your primary energy, in this case, uranium, and you go into heat, which is then transferred into mechanical energy, which is then transferred into electrical energy. All these transformations are not perfect and generate losses. If it's renewable, we can assume, to be simple, that what gets out of your renewable solar panel or wind turbine, we take that as the base. Of course, you can argue there is still a lot of losses, but that's where we start from. So we're much higher efficiency at that point. So when you look at a site and you say, I'm going to use electricity, it is important to see at that site, where does your electricity come from? And to look at the mix of that energy at that particular grid connection. So it's pretty important to calculate your energy, your total footprint based on where your energy is coming. Of course, now, if you go on site and you use gas or diesel burners, biodiesel burners, biogas burners, of course, your energy efficiency is 100% because you haven't transformed it yet. So it's still there. So there's no question of transformation, because the energy source you use is still the one. There's maybe a little bit of transportation, but that's not factor that in this. Now, second part is you have your energy on site. Now, how do you transfer that energy on site to the soil? So if you use electrical heaters, you have a pretty high efficiency. It's the joule effect. So you're close to 95% of that electrical energy that will be transformed into heat, and so transferred to the soil. Pretty high level of energy. If you go to direct fire heat production, so typically with biofuels or natural gas or diesel, you're much lower than that. with the conventional ones, the older ones, the ones we used a long time ago, we're about 35%. So we were almost as bad as electricity. Today, with all the versions and all the histories and the improvements, we're almost at 85%. That means that the amount of primary energy that is contained in, say, 1 cubic meter of biogas is almost completely transferred into the soil. Not completely, because there's still some losses and inefficiency, but most of it's achieved. So gives you an idea. This is what explains how come that this curve is so steep and got us in 25 years to where we are today, almost below the level of dig and dump. Third, last but not least, the losses at the boundaries. The losses at the boundaries, you'll see, they will depend on heating time and temperature gradient. Same thing as when we want to heat this room. If we put a lot of heaters in this room and we want to reach a certain temperature, once we have reached a certain temperature, there will still be losses through this wall. There will still be losses through the window that is open. We still have that. And that energy that is lost through the wall or through the roof or through the window is a factor of time on the one hand, and is a factor of difference in temperature. If it's the same temperature as outside, there's going to be no loss. The higher temperature in and the difference between in and out, the bigger the loss that there will be. So time is of essence in this case. And here is the formula for those of you who want to check it. But essentially, as you see it here, based on time, you see the longer it takes, the more kilowatt hour per ton we lose. And after a year or two, you almost lose more energy than what you need to heat it. So at some point in time, you have this is actually the curve or the line that proves or that shows that you cannot have an interdistance between wells that is 10 meters. Because as we'll see, if you reduce your energy density, so if you put your heaters or your heating elements farther away from each other, at some point your heating time will climb. And if your heating time if your energy loss is higher than the energy you need, you will never reach it. You will reach an asymptote. It's just like if you have too many windows open here, you cannot with one heater get to 30 degrees in this room. It will never happen. At some point, it will never happen. So that's part of it. So how do we reduce heating time? Because as we saw, the shorter the heating time, the less energy we waste, and so the more efficient we are. So of course, the time, keep in mind and remember, our goal here in thermal is to reach a certain temperature, and that's it. We're done. We don't have to stay there for another year. We just have to reach a certain temperature. Different than when you heat your house, you want to reach a certain temperature and then stay there for a longer time. Keep it at that. We just have to go there by and large, and then we can get out. So how do we do that? Of course, we can put more energy. So we can put like a bigger stove. One, instead of having a small one, you put a bigger one. That's one option. Or you can put more, of course, which is kind of the same. But you could also insulate better, so reduce your thermal losses. It's the same approach as when you want to reduce your consumption in your house. But the image I like is the leaking bucket. What does it mean? What we try to do in thermal is we have a bucket and it's leaking. There are holes. There's nothing we do. The holes are essentially the losses at the boundaries, the inefficiency. Okay, we can try to reduce those holes to a minimum, but there's only that much we can do. We cannot go further. And our goal is just to get that bucket full, and that's it. Once it's full, it's done. Okay, it can empty again. We have to reach the limit of the bucket. That's it. That's our goal. So you can see that in order to do that, you can have different sizes of faucet. You can have a small faucet or a big one. We all understand that if you have a big faucet, you will fill your bucket very quickly, no matter how many holes there are in. And yes, you will use less water. And with a bigger faucet, you will use less water to reach that full bucket. I know it's counterintuitive. Bigger faucet, less water. And in energy terms, the faucet is the power. So how many kilowatt do you have? And the amount of water is the energy. How many kilowatt hours do you have? So It's counterintuitive, but if you have more installed power, more watts, you will use less watt hours. I know it's like, what the hell? And that's why, because we don't have to stay there for a long time. We just have to reach there and then go. So that's why power is just the more power we have, the less kilowatt hours or the less energy we would use. So that's an important element to keep in mind: energy input and energy lost, right? And the energy loss, most of it we can't do anything. So we're going to focus much more on the incoming flow rate, because the leaking rate, there's nothing more. It's a given typically by design most of the time. So how do we minimize those losses? First thing we're going to do, we're going to insulate. We insulate more and more and better and better. And then we're going to go fast. These are the two elements. Same on the bucket. Try to get those leaks smaller and smaller, and then try to get the bigger faucet possible to get it to fill it quickly. Installation, we can do it at the surface. Try to do it as best as possible, because that's out of the 6 surfaces of our box. Remember, there's one that we can access, which is the one on the top. The other ones are pretty hard to access. Now, when we work ex situ, like in piles, then we can control much better, and then we can insulate all surfaces. So we can do it better. Now, even in containers, we work in completely isolated containers. You'll see that the energy is even much, much lower than that, because our installation is better. So that's whenever we can insulate, we do insulate. And then, of course, speed. Speed is, remember, the size of the faucet. The bigger the faucet, or the bigger the power, the more power injected, the faster we'll go. And actually, the lower will be our energy consumption. So how to increase speed? More power. So as I said, put bigger heaters, or put more heaters. Now, put bigger heaters, there is a physical limit. Soil can only absorb that much heat, typically 0.8 to 1 kilowatts per meter. So it doesn't matter if you put huge heaters in the soil, they will only deliver that much power to the soil. So there is a physical limit there. So the alternative then is to use more heating wells. So that's the alternative. So we will often translate that by energy density. As you can see here, there's an example where with high interdistance, so low energy density, so a small faucet in our leaking bucket model. And you have another one here with a much bigger density. So you could see that in some cases you have high interdistance. Here was almost 5 meters, and here you have 1.5 meter interdistance. You see, in some cases, that would be a little bit later in this presentation, there is justifications for going to one or the other of the models. Now, power input, that's the line I told you about. See, the more power, more interdistance, higher interdistance, so 5 meters in between. These are the two extremes you have. But on the one hand, we need way more power installed than in the other one. That's often the reason why we can't go for the higher density. So minimize losses, heating time, as I said. Here we have energy density, and here you have fuel consumption or energy consumption. So as you see, if you have high density, you're at 200 in this case, because your loss, the blue line is the loss, is pretty small. But the farther away from each other your wells are, the more your losses are, the higher your losses, and then of course, the more energy you use. So you still see at 450 kilowatt hour per ton when you have low energy density, low power, and you're at 200 with high power. So that's the illustration of what I said: more power, less energy. But the optimum is not just energy. The optimum is, drilling cost. It's good to have a high energy and high density and to have lots of heating wells, but drilling doesn't come free. And in the example I showed you, we have a 5 meter interdistance because the depth was 30 meters, 30. So drilling costs are more. So what you would save on energy, you would spend on drilling 10 times if we had chosen for a 1.5 meter interdistance with a 30 meter depth. So in that case, of course, we had a little bit more energy consumption, but it was more than compensated by drilling cost. But also equipment cost. If you have a lot of heating wells, you have more equipment. So it's also going to increase your cost. Of course, you have your scaling cost per unit. Yeah, panels and connections. The more you have, the more complicated it gets. And the attached labor cost. If you have to install 10 heating wells or 100, of course, all that is proportionate. And in the other direction, you so go your heating cost. Now, if you put all that into the same model, you will see that, and I'll just focus on those two curves. This is interdistance on the x-axis. Here you have interdistance. So high density here, low density here. Very small interdistance here and big interdistance there. The green line is the total duration, right? You would think it should be linear. It's not. Why? Because in this very high density, right, your heating time will be very short because you have high density, but your installation time and drilling time will be long. So at some point, it's if you say, I'm going to do a 1 meter interdistance and I'm going to be done in 2 weeks, and it's taking you 4 months to install all your wells, your total treatment time is 4.5 months, right? So it will go faster probably if you do a 1.5 meter, because you're going to heat a little bit longer, but you're going to save so much time on the installation and the drilling. So you see there is a minimum. But then if you factor all the other costs, here is the total cost. That's that blue line. I know there are many blue lines, but it's this blue line here. And you see that, of course, with high density, you have usually higher cost. It's very fast. That's the advantage, but it's higher cost. And with low density, you have higher cost as well. So on the left-hand side, it's more the installation and drilling cost that take the load on the cost. And on the low density side, it's more the energy that starts to kick in. So there is somewhere an optimum to be found, which can vary project by project, which needs and requires study, because as on the left-hand side is all these costs will vary from site to site, location to location, geometry to geometry. So that's a little bit, that closes the energy. And I just want to finish with one single case, which is the illustration of energy. Here is a site in Italy where we did about, this is the site where it comes, refinery, heavy oil. This is the condition when we got to the site. Pretty strict conditions on clean soil and pretty dirty soil. Part was 6 meters deep, the other part was 12.5 meters deep. Hydrocarbons, but also some chlorinated, chloromethane, chlorethane, some mercury as well. Not going to talk about the project and the realization. We did 24 batches, so in over 4 years. But I'm just going to talk about energy. As you can see here, high density. You can see different phases. Why different phases? Because that will optimize the equipment cost. You didn't have to purchase all the equipment. So that same equipment was reused from one batch to the other. And with, let's say, a couple of sets of equipment, we could do 24 batches. We didn't need to buy all that equipment, which again is a very important part of sustainability. It's not just throw it away. All of that equipment is reusable and has been reused. Here you have a good view of all these batches. This was batch 1 finished, batch 2 finished, batch 3 was in final approval and finished. In batch 5 was just dismantled, batch 6 was running, batch 7 was up and in preparation, batch 8 was in drilling, etc., etc. That's how it works. Bottom line, temperature reach 250 degrees, 35 days on average. Almost 1 million liters of oil recovered from about 160,000 tons of contaminated soil, because in this case, oil was condensed and sent back to the refinery, was in the refinery. And then, the numbers we're talking about, because at the topic, energy. Total 2.7 million cubic natural gas used for 161,000 tons treated. That's 171 kilowatt hour per ton. Remember, we calculated a theoretical consumption about 180. That was to reach 300. In this case, it's 250. And that was for 16% moisture. Here we got lower moisture. So we had a very low inefficiency. I think the theoretical number here was in the range of 150 kilowatt hours, which we were pretty close of with 171. But more important, it's 10 kilowatt hours less than dig and dump to 80 kilometers without treatment. So I think if you compare that, this was the proof that we could use less energy than dig and dump, and that we can, in particular, clean it, use less energy and still clean it compared to the alternative, which is just not cleaning. Quick conclusion: thermal desorption has become much more energy efficient over time. There's no needless to say, you could see it, this graph. It can be influenced and it should be influenced by design. As you can see, the interdistance will influence on your piping design. And first, reduce your energy and then use as green energy as possible. And it can be liquid or gas. They're all available on site, and it's pretty easy to mobilize wherever you. Isn't that's about my last slide. So I've been a little bit longer than expected, but
Yes.
I mean, I've been a bit longer than planned, not than expected. So thank you for it. Thank you for it.
No problem, Jan. Thank you for your interesting presentation. So now we will go to the Q&A session. So I see one comment from one yes. So he said only that apart from the number of heaters, the main thing is to have a good seal of the soil to be treated so as not to lose heat and increase the heat in less time.
Yeah, absolutely. I think it's a very good point. Very that it was about the losses. Essentially, the volume in situ, even better when it's ex situ, although then you have to excavate. But everything you can see that you can close is energy that doesn't go up. So that's how you reduce the losses. Unfortunately, when you do it in situ, there's not a lot you can do other than seal the top. We are working at trying to seal the sides with even thermal insulation, like kind of keeping that thermal different, that gradient a little bit lower, but there's not that much you can do. And that's also what explains if you do the math and you look at the numbers, the deeper we treat, the lower the consumption. Because of course the volume is then more advantageous. That's also why in situ is hard to apply when you have like say 1 meter thickness or depth, because then your surface is huge and you have a lot of losses. So, but it's a pretty good point.
So yeah, there is one more question. So do you encounter soils that are co-contaminated with both metals and organic pollutants?
Yeah, good question. Yes, we do that. First, some comment on metals. So what we will consider metals here is all heavy metals except mercury. So let's consider we have organics, which is typically something that thermal does. Mercury, which is what the only metal that we can treat with thermal, and then we have the other metals. Yes, we've encountered many projects where you had organics and metals. Can we do it with thermal? Yes, but we don't treat the metals. It's pretty simple. Metals will not be treated with thermal. They won't be hurt as well. So by and large, you'll have as much before than after. It doesn't bother us. We'll take out the organics and we'll leave the metals. Usually the risk pattern for metals is not the same as for organics. In many cases, organics is the focus more than metals because organics is more mobile and needs treatment, but it doesn't cause an issue if they're there, but we can't treat them. Other than mercury, which again, it's the only volatile metal.
Okay, thank you. One more question. So can you control the evaporation temperature in order to separate different evaporable compounds? In the case of hydrocarbon, how was the oil recycling process made?
Yes and no. I mean, it's temperature. So in other words, if you reach temperature, you will vaporize everything that is in vapor condition at that temperature. There's no way to separate and say like you would do like you would do a still and just say I'm gonna just extract this, put myself at the right temperature. The reason we do that is that the whole volume is not at the same temperature at the same time. Close to the heaters, you'll be already at high temperature, and the farther you go from the heaters, of course, you'll be at lower temperatures. So you'll start to mobilize some contaminants at closer to the heater and not yet farther. So we take everything. In other words, and how does the oil recycling process work? In the case I showed you, in most cases with mixed components, it's by and large condensation. So it's trying to heat it up to separate, to mobilize, separate from the soil. And once you have separated them, then it's condensing them to get them back in liquid phase. When it's pure hydrocarbons, we apply the reburn process. And that reburn process is essentially still mobilizing them, transferring into the vapor phase, getting them out, and then the vapor, instead of condensing it, use it directly as energy in the same burners. So zero waste and 100% recycling of the contaminant itself because it's energy in the first place.
Okay, Thank you. One last question, maybe. How do you manage odors? Is the vapor treatment integrated in your system?
Yes, of course. There are two ways to manage odors. The first is the fugitive ones. The first is your volume when you treat always needs to be in negative pressure. So the vapor pipes that are just extracting it, they always have to be under negative pressure to make sure that any vapor you create in the process, which is the whole purpose of it, is funneled through the vapor pipes and in the system and doesn't go wildly above ground. It's key to make sure that there is no odor. So the whole thing has to be under negative pressure. The sealing is not so much the containment of the odor, it's really the vapor, it's really the negative pressure. And then of course it's how you treat it in a well-designed vapor treatment unit, right? So whether it's condensation, carbon, catalytic oxidation, it doesn't really matter as long as it's sealed and it's treated, and then the exhaust is controlled, of course.
Okay. One last. So one person that say thank you for your answer. And
Welcome.
but did you think about remediation trends for co-contamination soil? We are small, highly innovative SME. Oh, sorry, I cannot read it. SME, which develop advanced soil washing technology for removing metals and metalloids from soil, and we would be interesting to cooperate with your company.
Well, thank you. I'll recommend you to get in touch with us just after this webinar, because we see, and I think we made a webinar on the PFAS treatment, but we see pretty good cooperation between soil washing and thermal. We've done it for many cases where indeed soil washing can treat something, can already take out metals, and then we would just address thermal, for example, in the soil washing cakes. So that there definitely can be pretty good combination about it.
Okay, there is a lot of questions, so maybe 2 minutes is remaining.
Yeah.
So maybe one more. Do you have any feedback on the treatment of PCB?
Yeah, a lot of it. The PCB is typically something that is treated by thermal because it's volatile, 320, 350 degrees, pretty similar to dioxins, for which we also have quite a bit of I think you worked on dioxin project as well. By and large, PCBs are volatile at 320, 330 degrees. We heat the soil, we extract the PCBs, and then there are two options with PCBs. The first one is the conventional condensation adsorption, so bringing them back into, at the end, absorbing them on carbon, and then using the carbon as waste of the system that goes for further treatment to the incineration plant. The other one is what we applied, and you've been on that site, what we applied for dioxin when we think we want zero waste, and then the PCBs that come out, the vapors are immediately sent to a thermal oxidizer and destroyed at 1200 degrees for 2 seconds, so that there is zero waste at that point. So there are two options. The one is a little bit more costly, but more efficient. And the other one is a little bit less costly, but you're dealing with waste which you have to then dispose in a second stage. But yes, PCBs is a very common contaminant that is treated by thermal.
Okay, so the last one question.
Oh, it's the fourth last question.
Yes, exactly. So in 1 minute, what is the effect of the uniform heat distribution, for example, conductive vs ERH, on treatment time and hence heat loss?
So there is a factor. So I think the point is ERH is heating more. ERH is electrical resistive heating for those who follow us. So it's essentially injecting actual current in the soil and use the soil as a resistive body, so that by the Joule effect in the soil is heating. So first, to be sure, to be clear, ERH does not go above 100 degrees because ERH needs moisture to conduct the heat. So there's no way you can go above. So, but for low temperature, what's the difference? There is an overheating in conductive that you don't have in resistive, because of course conductive is by contact. So your heater wells will be always at a higher temperature than your target temperature. So if your target temperature is say 100 degrees, you still start at 400 and you stop when you reach 100 degrees at the cold point. But in the meantime, you have had a certain part of the soil that has gone above 100 degrees. So you have a loss there, which is true. You have a loss there. It's typically anywhere between 10 and 17%, I think, according to calculations, of total energy that is actually overheating, overshooting the target temperature because you're closing to the heating well. So yes, that's the point. Conductive heating is not homogeneous. It's always hotter, close to the heating elements, and colder to the core point. Same as if you heat this room, it's thanks to convective effect that you homogenize it, but it will still be hotter close to the radiator than in the center of the room. So yes, indeed.
Okay, thank you, Jan. So this is
You're welcome.
this is the end of the webinar. So thank you for your attendance and your question. You will receive the recording of the webinar and also attendance certificates. Thank you, Jan, for your presentation.
Just to add that, well, thanks for hosting me. And yeah, if there are more questions that we couldn't answer because of time, still put them there, and we'll take care of written answers to all of you. And
exactly. Thank
see you next time.
Yeah. Bye bye.
Bye bye.